the paradox that forced mathematics to start over. It looked like a clever definition. Then it broke everything. To understand why mathematics was forced to rebuild itself, we have to return to a moment when confidence was at its peak. By the late 19th century, mathematicians believed they were close to completing the system. Every concept could be defined. Every truth could be proven. The foundations felt solid. This mattered because mathematics was no longer just abstract thought. It underpinned science, engineering, and logic itself. If math was consistent, then knowledge was secure. If it failed, everything built on top of it trembled. The paradox emerged from an innocent question about sets. Collections of objects defined by clear rules. Sets were supposed to be safe. They organized numbers, shapes, and ideas cleanly. But one definition quietly crossed a line. It asked whether a set could contain all sets that did not contain themselves. At first glance, this sounded abstract but harmless. Yet the moment it was examined, contradiction appeared. If the set contained itself, it shouldn't. If it didn't, then it should. There was no escape. Logic folded in on itself. Proof collapsed. A single definition had exposed a flaw at the core of mathematics. This was not a technical inconvenience. It was an existential crisis, and it forced mathematicians to confront a terrifying possibility, that certainty itself might be unstable. The immediate reaction was disbelief. Surely the paradox was a trick of language, not a real mathematical threat. But every attempt to patch it only revealed deeper cracks. The problem was not the question. It was a freedom allowed in defining mathematical objects. Until then, mathematicians had assumed that any clearly described collection could exist as a set. This freedom felt natural. It matched intuition. But the paradox showed that unrestricted definition led directly to contradiction. Mathematics could not allow everything it could describe. This realization spread anxiety through the field. Proofs built on set theory were suddenly suspect. Results once considered airtight now rested on unstable ground. The discipline that prided itself on certainty had discovered a self-destruct button. Some tried to isolate the paradox and move on. Others argued it was a warning that could not be ignored. If one contradiction existed, others might be hidden. And if contradictions were allowed, then any statement could be proven true. Mathematics would lose meaning entirely. The conflict was no longer abstract. It was practical. How could one trust calculation, theorems, or models if their foundations were compromised? Progress slowed. Debate intensified. Entire programs were put on hold. The paradox had done its damage. It had revealed that mathematics needed rules not just for reasoning, but for existence itself. The conflict reached its peak when mathematicians realized there was no simple fix. The paradox could not be ignored, reworded, or safely contained. It demanded a choice. Either restrict mathematics or accept contradiction as a permanent feature. Some proposed rebuilding logic from the ground up. Others introduced strict hierarchies, carefully limiting which sets could exist and how they could be formed. New axioms replaced intuition. Every assumption had to be justified, not felt. This shift was painful. Elegant arguments were discarded. Intuitive shortcuts vanished. Mathematics became more formal, more cautious, and slower. But it also became safer. The freedom that once allowed creativity was now seen as a risk. The emotional core of the struggle was lost. Mathematicians had to accept that not every question could be asked meaningfully. Some definitions were forbidden. Some ideas were declared invalid, not because they were false, but because they led to contradiction. Yet something unexpected happened. By limiting what could exist, mathematics gained clarity. Structures became cleaner. Proofs became stronger. The discipline matured, aware of its own fragility. The paradox did not destroy mathematics. It humbled it, and humility turned out to be a foundation stronger than certainty. The resolution arrived when mathematics accepted a hard truth. Absolute freedom was never compatible with absolute certainty. By choosing consistency over intuition, the discipline secured its future. New foundations emerged, built on carefully chosen axioms. These rules did not claim to describe all possible truths. They described a safe framework where contradiction could not spread unchecked. Mathematics stopped asking whether everything imaginable could exist and started asking what could exist without breaking the system. This change reshaped how knowledge itself was viewed. Proof became conditional. Truth depended on assumptions. Certainty was no longer universal. It was local, precise, and earned. Far from weakening mathematics, this made it stronger. Engineers could trust calculations. Scientists could build models. Logicians could explore limits without fear of collapse. The paradox had drawn a boundary, and boundaries created stability. Today, that lesson still matters. Systems fail when they allow unrestricted freedom without safeguards. Rules are not enemies of creativity. They are what make creativity survivable. What forced mathematics to start over did not end its story. It refined it. Subscribe to join the journey.